Welcome to the second part of the video about the fundamental theorem of calculus. If you haven't seen the first part, I would suggest you to look at that first part before you watch this video. Alright, so now we have the following problem. We want to compute the derivative of this function. Well, it seems this integral is exactly like what we did before in the first video. So what is the big deal about it? We need to be careful here. In our previous examples, all the lower limit of the integral is always a fixed number, like 3, 5, 1000, 1 million, 0, etc. But here, the lower limit is another function of x. So how we can deal with that? Well, the answer is obvious. We need to somehow force this integral to have a lower limit where the lower limit is a number. And how we can do that? So remember that we have the following property of integral. If we have an integral from a to b, we can split this integral from a to c and then continue from c to b. Okay, so let's try apply this property to our problem. So using that property, that integral property, we can split the integral from x squared to c. What is the c here? Well, you can pick any c. You can pick 1 million, 5, 3, but let's stick with 0. Square root 1 plus sine t dt. So from x squared to 0, and then we continue from 0 to x cubed. Okay. Now let's analyze our integral. So we will be able to compute the derivative of the second term by using the method which is exactly the same like what we had on the previous video. Okay, because here we have a number on the bottom and a function on the top. But unfortunately, we cannot right away using the same method for the first integral, because on the bottom we have a function and we want to have a number on the bottom. But that's not a big deal. We can always switch the limit of integration provided that we put the negative sign in front of the integrand. Okay, now we are ready to compute the integral. We are ready to compute the derivative. So first, what is the derivative of the first term? Okay, the derivative of the first term is simply we can obtain by simply substitute x squared for the t minus square root 1 plus sine x squared. But don't forget, we need to multiply by the derivative of that guy. Multiply by the derivative of x squared is 2x. Similarly, the derivative of the second integral, we can obtain that by substituting x cubed for the t, and then after that we need to multiply by the derivative of x cubed, which is 3x squared. And we are done. Okay, now look at the following problem, which is kind of different, but we still use the fundamental theorem of calculus. In this example, we want to compute the limit of that function. I'm sorry, this should be x cubed. Okay. So how we can compute this limit? Of course, the first step is always trying to plug in x equals 0 to that expression. Okay, let's try. What happens if we plug in x equals 0? We will have, okay, if we plug in x equals 0 to the top, we will have 0 to 0, okay. But remember that one property of the integral says that the integral from a to a will always give 0. Okay, so when we substitute x equals 0 to the numerator, we get 0. And likewise, if we substitute x equals 0 to the bottom, we get 0. That means this limit is of the type 0 over 0. And what is the powerful tool that we can use if we have a limit of the type 0 over 0 or infinity over infinity? That's right, we can use the L'Hopital rule. Okay, let's put that L to denote that we apply the L'Hopital rule. So the L'Hopital rule says that since this limit is of the type 0 over 0, then if the limit exists, it will be equal to the limit of the derivative of the top divided by the derivative of the bottom. But the derivative of x cubed is simply 3x squared. Now the fundamental theorem of calculus come into play. The derivative of the top, we can compute that by using the fundamental theorem of calculus. So what is the derivative of the top? It is simply sine, substitute x for the t, sine x squared. And we can also use the same kind of thinking that we multiply by the derivative of that expression, but the derivative of x is just 1, so then the derivative, then the numerator is just sine x squared. Okay, limit x approaches 0, the derivative of the top is sine x squared, and the derivative of the bottom is 3x squared. Plug in x equals 0, we have 0 on the top. Plug in x equals 0 on the denominator, we have also 0 on the denominator. So it means that it is still of the type 0 over 0. We can take another L'Hopital rule, take the derivative of the top, which is cosine x squared times 2x divided by 6x. Okay, we can simplify this 2x over 6x as 3. 2x over 6x is 1/3. So now, as x approaches 0, the top approaches cosine of 0, but cosine of 0 is 1. So then the final answer is 1/3. Alright, that's all for now. Thank you for watching. See you later.